Okay. As we saw in the hello to everyone. As we saw in the first two sessions in the talk, they talk about the magnetic field effect, and today I will try to talk about the electric field effect or electrostatic field effect on the ion channels, especially on the leak potassium channels. My talk deals mainly on leaks potassium channels because the importance of these channels is in the anesthetic materials. Actually, they block some of the anesthetic material and the effect on the action potential. The action potential constitutes the signal by which the brain receives, analyze, and convey information to the brain. This action potential consists of two main phases. The first one is the depolarization. First one is depolarization, and the second one is the repolarization. The depolarization is composed from opening of sodium-dependent potassium sodium channels, and the second one is potassium-activated channels. And the last phase is the leak channel. The leak channels, I will try to focus on these kind of channels. Actually, all the potassium channels consist mainly two main channels. And I will try to talk about the voltage-dependent potassium channels, the first one, and the last one, the leak potassium channel. If we think about the leak potassium channels, it sounds as that they are leak channels. It means that the potassium passes across the channels as a leak. But actually, it's not. When we look, in order to open these channels, we need to change the voltage. But let's start from the beginning and talk about a little bit about the voltage-dependent potassium channels. These voltage-dependent potassium channels, they have a canonical. Try to find it. Okay. They have a canonical voltage sensor. It means when the voltage, sensor sense the change in the voltage in the membrane, it moves to this part, and the potassium ion can pass across the channel. When it's open, as you can see here, they release this part of the channels, and the ion can pass across these channels. These kind of channels you can see here. As you can see here, this part of my experiment in the past. You see the movement of the charges and loading the membrane, and you see here this depolarization, and this phase is closed channels, as expressed in the current with the Boltzmann curve. You can see that this is the closed state, and this is the open state, and between them, the states that occur between them. When you talk about the leak channels, actually the story is totally different. As I said at the beginning, leak channels, it's called leak channels, but actually most of the time they can open only with a voltage sensor. As you can see, for example, in this phase, you can see that they open and close. These phases belong to the leak channels, and you see that this phase can it's voltage dependent. But the problem of these channels, there is no canonical voltage sensing. Okay, this is one of the problems of these channels. It's very small channels. It's smaller than, for example, than the voltage-dependent potassium channels, but they don't have any of the voltage sensing. So when I was a couple years ago in the Stephen Tucker laboratory in Oxford University, I thought about idea, where is the voltage sensing they sense? At the same time, they just finished a project to find where is the voltage sensing of this kind of channels. So they found some But before that, this is just a proof that you see that these channels open with the change of the voltage. So in order to prove that these channels open in sensing the voltage, what I did in the past, you can see that I actually constructed a chimeric channel that composed from voltage dependent potassium channels and leak potassium channels. It means that I took the part with the voltage sensing and composed it to this part, and actually I built a chimeric channels. Actually, I did it with genetically, and finally I measured it with electricity, with the current that passes across the channels. I think I composed something like maybe 50 chimeric channels. Only small part of this kind of channels work. It takes a couple of years in order to build this construct. And as you can see, it means this part of the channels, I mean the pole where the potassium pass the channels, it senses, there is something that senses it. So when we think about this kind of leak channels, so I still don't have the answer. Where is this voltage sensing part of these channels? So when we look on these kind of channels, actually these channels can open and close, means the gating process, it's almost from everything. It can be opened by acidity, it can be opened by the stretch of the membrane, it can be opened by a change of the pH. Almost every material can open and close these channels, block these channels. People talk here about the zinc. So I made some experiments in the past with the zinc, with the lithium, almost everything. So it means that there is something that affect on these channels. So where is the real voltage sensor of this channel? So as I said at the beginning, part of my background of this work is came from the lab of the Stephen Tucker Laboratory, Oxford University, that he published this paper. And he thinks that there is very tiny voltage sensing inside the channels. Means he didn't say that in this paper, but I thought about it, that maybe there is electricity field from inside to outside. I'm not talking about this part or this part. I'm talking about this part. Actually, they made some mutations in this part, and these mutations maybe gave them the clue, the first clue for sensing in this part of the channels. In my experiments that I did recently, actually in the last 2 years, I found very interesting results. First of all, I found that there is some, I will show you this is the model, but I found, first of all, I found that there is some differences between this part of the channel. Actually, this part is natural, and this part of the channel is charged, and also with this part. And I mean that maybe I thought maybe the electricity the electric field come from here, and each molecule that just enters to the cell, not to the cell, to the tissue, just outside of the tissue, they change the electric field here, and they cause to open to the channels. And if you look on, for example, on this model, you can see this is the electric field. And each molecule that can just touch in this area can affect on this part of the channels, and of course to open and close these channels. One of my experiments that I did here, and this experiment I did at Stephen Tucker Laboratory, and I checked the electric field and the potassium entrance to the cell. And you see, as long as we we close to the path of the ion conduction pathway, where there is more potassium that enter to the cell. For example, if we, I mean that there is a picture here. It means if I'm doing, I did it with two sides. It means when we are working in this part, it means the effect is less than to this part, because it's the density is bigger here. Okay. So recently, I found actually two different channels. One of them is a channel. I'm talking about the leak channels. Two type of leak potassium channels. Two type of potassium leak channel. The first one is it's often most of the time. So what I found in this type of channels, that as I said in the beginning, the charge, there is more charge in this part and in this part. So what I did, actually, I changed the amino acid in this part, and you can see the differences between the voltage dependent, okay, in each channels. I changed it to, for example, I took channels that it's much more, they have much more charges here. So I replaced it to natural amino acid here and here. And with the channels that they have less, I changed it to the much more charges natural much more charges amino acid. And as you can see, the effect here is lower, and the effect here is bigger. So to conclude my lecture, I can say that first, these results I got 6 months ago. Okay, it's a new one. It's not published yet, so I'm very happy with these results. And it means there is some clue for existing of amino acid that charged amino acid here that caused change in electric field. And what is very important in these results is that think about that there is that each of the side, I mean this side and this side cause electric field outside, and each molecules that just want to enter to the cell, to just enter to the, to the tissue, they feel they feel, I mean, they feel it, and they change the electric field and cause to the gating process and open and close the channels. And that's all. Thank you.
Thank you very much.